Good evening, one and all. This is Dr. Ramakrishna, co-coordinator along with Dr. Raghu Kumar, coordinator of this wonderful learning program. Welcomes you all to another informative and exciting session on day 2. In these 2 weeks, AICTE sponsored Atal FDP on applications of IoT in mechanical engineering. Today we have an young and dynamic speaker, Dr. Debashish, who is contributing so much to the research community in this field of research on IoT in mechanical engineering. Dr. Debashish has bachelor degree in mechanical engineering in the year 2013 from the Biju Patnaik University, and then masters. After that, he went for the PhD program in the IIT Institute of Technology, Kharagpur. After his doctorate, he has worked for a short-term researcher at the Center of Excellence in Advanced Manufacturing and Technology of IIT Kharagpur. He is presently working as a postdoctoral researcher at the University of Connecticut, USA from January 2022. His research work focuses on the applications of real-time monitoring and control in manufacturing processes. He has developed an industrial 4.0 model for the friction stir welding process along with the personnel of Tata Consultancy Services Research and Innovation. He is also a author for one textbook, and he has published several articles in international and book chapters as well. He is also filed 4 Indian patent applications on the application of signal processing, machine and learning methods in manufacturing. With this brief introduction, I am handing over the session to Dr. Debashish.
Thank you, Dr. Krishna. And I'm also very much thankful to Dr. Kumar, the head of the department of the institute, the head of the Department of Mechanical Engineering, for putting up a program like this. And let me share my screen. So the title of my presentation is Manufacturing Process Monitoring. And as you can see in this slide, I have put a very high-level picture of what we today call as the smart manufacturing. On the left is the picture representing the manufacturing shop floor, and the data in the form of barcode, which is being sensed through the various sensors, and there are all embedded devices in the manufacturing shop floor, and this all data is being analyzed, processed, and given us as insights on the right hand side, the activity dashboard. So what happens inside between this activity dashboard, which shows the insights, and from the data that is being collected from the manufacturing shop floor, is altogether known in chunks like the IoT devices, the connection between them, the processing of information, and altogether the applicability of the cyber physical system. So in this 40 to 45 minutes presentation, my objective would be to showcase you the devices, how they are connected, how the data is being collected and processed, and finally we get the real-time inferencing on the activity dashboard, which altogether gives us a good idea of the application of IoT in manufacturing. So this would be the 4 areas where I would mostly focus on. The first is why we need to worry about process monitoring. As mechanical engineers, we have different domains. I would mostly be speaking on the manufacturing side. So when it comes to manufacturing, monitoring becomes very important because we have the complex processes, and within the complex process there are various small attributes, and each of the thing, if monitored and controlled in a manner, if we know the real-time information, then we could track things better, we could make profitable decisions, and also we could enhance the productivity. The second part would be how we can do the monitoring, how to achieve the real-time monitoring and thereby control the process. And in this process, how to make use of the IoT devices, the cloud, the edge devices, and the communication between all those devices. For these examples, I would be using various case studies. These case studies are part of my research work, and they are mostly in the manufacturing domain. And finally, I'd give a way forward to conclude the session. So I would begin with the introduction to Industry 4.0 and thereby the Internet of Things. And for this, let me take you a little back in time to the pre-industrialization period. And in those times, the manufacturing mostly happened at homes by the skilled artisans who performed the manufacturing. So they had their own handmade goods. And that continued for years when the first ever steam engine was introduced. So people then realized that the power that could be generated by driving the steam can also be used to run the machines. And then the people realized that it is much less expensive than by using the power that is generated from the steam driven engines, or in place of using the human strength or the animal strength that was used for years. And that introduced the idea of productivity in manufacturing, because people realized that by using that power, they could do more work by running the machines than by using the animal or muscle strength for uh, many number of days. So that use of the power that was generated by driving the steam brought a change, a paradigm shift in the industrial context, and that was known as the first industrial revolution, or the Industry 1.0. The second industrial revolution is largely known for the introduction of the moving assembly line by Henry Ford. So if you consider the first industrial revolution, the job was fixed. All the machineries, people, and other things were brought to the job for working on it. So it can be called as a job-centric scenario. But if you look at the second industrial revolution in the moving assembly line, it is like a transfer line. The product which is being manufactured is constantly moving on the transfer line, and on the either sides we have workstations that divided the machineries. So each workstation is now performing a specific job, and there was also the division of the labor, the people that were doing the job. So this what happened. The product is now moving on the transfer line. So they further enhance the productivity with less number of men, and they introduce the interchangeable parts. Now the dimensions are going to be similar, and the products are going to be much more dynamic in nature. The third industrial revolution started with the introduction of the IT communication. Computer is also known to be introduced in this area, in this particular era, and most of the NC, CNC, and what we use most of CAD, CAM, and SIM are all a part of the third industrial revolution. So the large-scale automation of manufacturing actually began in this era. The robots were also introduced in the third industrial revolution, and they were mostly used or ushered in the automobile industries, and one of the major manufacturer of automobile, Ford, was using the robots in their industry. So automation in the manufacturing, the use of NC, CNC, programming, coding, all those things began in the third industrial revolution itself. Finally, we are here at the fourth industrial revolution, or which is known as the Industry 4.0. And the Industry 4.0, the main target or the buzzword is the connected manufacturing. So what it uses is how can we connect devices together so that we can share the data between them, and by sharing the data, we could have the meaningful information communicated between the devices, and those meaningful information can be used to note the real-time operations of the process, maybe it the health of the machine or the product that is being manufactured. And this could be, and this is established with the help of the Internet of Things, that is the devices that are embedded in the manufacturing machines or associated with the machines, through the use of cloud, where the data is being communicated, and integrating the physical device with the cyber world, which is known to be the cyber physical systems. So if you see the change of things from Industry 1.0 to 2.0 to 3 to 4, the manufacturing concept remained the same. What is being changed over the year is the way we do the manufacturing. So productivity, ensuring the quality, the accuracy of the information and the product is all remaining the same, but the way we do the manufacturing is changing over the years. At present, we are mostly concerned with the data. So the data, the information, how can we collect from the machines, how can we process it, how can we communicate it, and how to derive the insights in a manner that is meaningful for the industry is all about the smart, smart manufacturing or the industry 4.0. So the industry 4.0 is a concept and it considers several components. And as I've shown a picture here, there are components like the Internet of Things, which is about the connected devices, the intelligent devices. It could be the sensors, the computers, it could be small computing device, large computing device. And how do we use this information of the Internet of Things, the connected things, is by connecting them to edge devices or the cloud devices. The computing that we are doing in the cloud devices is known to be the cloud computing. And because we are talking about manufacturing, there would be the big data. What we refer as big data is data can be uh, seen as a four V's: the velocity, the volume, the veracity, and the variety. So if you're concerned about the manufacturing process, we know it is referred to as a complex because it consists of various small attributes. So it is not possible to have include just one sensor or one device and do the entire processing of a manufacturing process. So we may need large number of sensors, and those sensors would differ on the way they are positioned, on the way the data is being collected. So we would require a large volume of data to process the information. That's the volume. Now every data would be coming in different sampling rates, different variety, and the information may be processed in different manners. And that's where the term velocity comes into. Variety is because we may be having 1D sensors, 2D sensors, or maybe the 3D images which may be captured for different attributes, for different reasons. And that's gives the variety in the V. And finally, we need to have the meaningful information of the data, and that's why we have the veracity. So all these four V's gives us the big data concept for the industry 4.0. We have the cyber physical systems, which means that the physical part, the physical machine, the physical sensor that is being collected, the data, it is only meaningful or it will only make sense if we can derive some meaningful information out of it regarding the process, regarding the machine, or regarding the thing which we are targeted. And how that information, the derived decision, can be again fed to the machine. That's a feedback connection from the cyber part to the physical part, makes it the cyber physical system. And of course, there are other things related like the entire integration of the system. So there is a system integration. We could also simulate the things to know what could be the what if scenarios with the process. There is additive manufacturing, and with all this, because we are mostly dealing with the internet, the data communication, cyber security is going to play a very important role. So it is very important for us to make use of communication systems and algorithms that are secure in nature. So just to give a small idea about how people are looking at the Internet of Things, this is one definition which is given by the Forbes. So it is a concept of connecting any device to the Internet. So our TV that we are mostly using nowadays, the smart TV, can be called as an IoT device because the smart TVs are connected with the internet. That means when we switch on our TV or when we switch on an app, it has the ability to communicate the data to their server. So if you consider the Netflix, we are getting when we are watching any app or any the Netflix app and we are watching the movies or streaming videos, it is always communicating some data to the Netflix server, and that's how the Netflix server gets the customized information about the user, that what sort of videos or what sort of movies he's liking to watch, and that's how they recommend us the next videos or next ads or things like that. So any device which is able to communicate to the internet can be referred to as an IoT device. because it has the ability to share data, and when you have multiple devices communicating information between each other, they can be referred as the IoT nodes or a network of IoT devices. When it comes to the context of applying to the industries, the devices that we are to be used as the IoT device, we know that they are to be rugged, they are to be much more rugged from the traditional devices, because they are to sense in an industrial environment, and that's why the IoT, when it is applied to the industry concept, we refer as the IIoT, or the Industrial Internet of Things, and that focuses mainly on the use of the cyber physical systems. As I told, we have to have the cyber part, or the cloud, or the edge devices, which could make the meaningful decisions by working on the data, and thereby the feedback can be fed to the physical device, making a tight integration between the physical and cyber part. So when the physical systems are made intelligent, the real-time communication and cooperation can be built among themselves, leading to the smart factory. So there could be various applications of IoT in manufacturing. I have listed 4 major applications. The first is the real-time product quality analysis. As I told, we could have different sensors that could be embedded in the manufacturing process. Now those sensors, what sensors we will be choosing depends on the process, and that data, if you can take and communicate and derive the meaningful information, we could do the product quality analysis. We could also do the predictive maintenance and health monitoring. Similarly, we could operate so why we need to worry about the process monitoring of the manufacturing process? And here I have a small story to tell you. And this story is about the X Coffee, the Trojan room coffee pot. And the origin of this story is from the University of Cambridge, and they have a computer laboratory. And this story is narrated by James Quentin Stafford Fraser. He is a computer scientist and entrepreneur. So what happened is, they had a lab, this computer laboratory, and there were several people who were working in this lab. And there was a coffee pot. So like we have different labs, but there is only one coffee pot. So all the researchers who were working at the night time were all dependent on this one coffee pot, similar to like our chai stalls. And there were other group members also who were also the other lab members who were also dependent on the coffee pot. So, and approximately the coffee pot, it took around 5 to 7 minutes to brew the coffee, because at that time there was no instant coffee, so brewing was the one thing that was used there. So what happened is, the people always had a problem with this brewing thing, because whenever somebody wants to have a coffee, if the coffee is not brewed, then they have to take a 7-minute walk and then come and see that the coffee is not there, and they get distracted, they were irritated, and they went back, and they were all facing a similar problem with this thing. So one of the scientists, James Quentin Stafford Fraser, along with his friends, what they do is they put a video frame grabber, one of the old camera system that was available in their lab. They put it in front of this coffee pot. They made a stand. Now the video frame grabber was capturing the video of the coffee pot. They wrote a client server program. So the client itself is the video frame grabber, which was connected to one of the IP system, and the server were the different computers that were associated for the lab members. And they developed an application which is named as the X Coffee, and that's why the name of the story is X Coffee. So through this application, whenever somebody wants a cup of coffee, they need not to walk for the 5 to 7 minutes time to the coffee pot, but they always now look at this application and they get to know whether the coffee is available or not, and accordingly they made a decision whether to go or not. Now this simple idea is what we know as the monitoring, and the benefit which caused them is that it saved their time, they were less distracted, so whenever they need, on the basis of the need, they did it. So if we take it forward to our manufacturing scenario, the coffee pot is the manufacturing process that we want to monitor. The video frame grabber is the sensor. So we have the sensor now, which is looking at the manufacturing process. The client server program is the signal processing or the modeling, which is collecting the data, which is acting on the information. And finally, we have the application. The Xcopy application is our decision. And what this represent? If we look at the manufacturing process, now we need to identify that what exactly we need to monitor. For a coffee pot, it is very simple. It is just whether the coffee is there or not, whether the coffee brewed or not. But when you say about the manufacturing process, as I always told that there are several attributes which are concerned with the manufacturing process itself. So we need to identify that what is the thing that we are going to monitor. And once we identify our objective in the manufacturing process, accordingly we have to decide what sort of sensor would be best suited for that application. Whether it would be contact type sensor, whether it could be non-contact type sensor, or how the sensor has to be designed, several such things like that. Once we have the data, once we have our objective, we could design the experiments in a manner and we could operate on the data to derive the meaningful information out of it. Now this information derivation has to be done through various signal processing techniques, various machine learning models, depending on how the information is there and how do we want to model it. And of course, at the end of the day, this information can only be said meaningful if it makes meaning to the operator who is operating on the machine, how with ease it can operate it. Finally, we have the decision in manufacturing is that whether the quality of the product is good or bad, whether the machine can be operated or not, whether do we have faults in the process or not, things like that. So what is the benefit in the manufacturing is that we could detect the faults, we could predict the quality of the product in real time, and accordingly, with all these things, we could make profitable decisions. Now the decisions is not only in terms of fault or predicting the quality, but we can also make use of the management things like how can we take a decision on our inventory, how can we have the raw materials beforehand, or how can we control the inventory management in the company. That could also be another benefit. So taking this entire scenario, the video frame grabber, the small computers that were processing the information, they're all small because they were smaller computing devices. They were not exactly computing anything, but it was just a client server program which was collecting the data and was showing in other applications. But if we think of the manufacturing thing which we are talking about, there we need the sensor and also with some computing power so that we can process the information. And altogether we can say there would be these are the IoT devices because they are connected to the internet, they are sharing the data, and that's how this would be our ecosystem for the IoT. But another important thing that we have to also take into consideration is the cyber component. That is because here there is no processing of information or there is no requirement of a feedback to the process, but in actual manufacturing scenario, we would also need a feedback that would give us an idea as to how to prescribe the decision that is taken. For example, if I say the quality is bad, so what I need to do, whether I need to change the settings, whether I need to discard the product, or there could be some other prescription, and that prescription is generally comes from the cyber part who is operating on the meaningful decision. So what is the theme for the process monitoring? So now as we have this idea that why the monitoring is required, how do we do the monitoring? So we have this DIKW pyramid, which stands for data, information, knowledge, and wisdom. And this is in form of a pyramid because we start from the bottom layer, and that's the data. And for data, we need to have several sensors, the IoT devices that are associated, connected, or installed in the manufacturing system. And once we have this data, we need to operate on the data to derive the signal informatics. And this informatics would make sense because we have to always go a back forward, a downward approach. We have to connect to the data that we are capturing. And when we have all this information, we need to make the interpretation. The interpretation can be in form of modeling. So when you have the signal processing thing developed on the data, having the meaningful information, we could automate the process by using the machine learning models. So once we have the machine learning models ready, we have automated the process, then we could have the insights or the application in form of the dashboards that can show the idea to the insights to the operator. The most important thing to mark here is that domain knowledge is very important. And why I say domain knowledge is every manufacturing process is different from one another. So what sort of sensors would be required to get the data, how the information is to be processed, how one would choose between the models that are available, or how one would choose the signal processing techniques, or the information that has to be processed depends on the domain expertise. So if we do not have the domain expertise, then the modeling may not make sense to the operator, or it may not be meaningful to the entire DI-KW pyramid. So if we take a small example, is that the relation between a patient and a doctor. So Mr. Y is the patient and Dr. X is operating on the patient. So what the doctor collects the primary information from the patient is the sound with the help of its stethoscope, which is a classical example of a sensor which is being used from so many years. So that sound information that the doctor collects, he processes it, and the sound can be processed based on his expertise. And once he processes the sound, it gives the doctor a multitude of what if scenarios, that what could be going wrong within the human body. And once he has all this information in hand, it further narrow down his research by prescribing him few tests, and that's how he goes deeper into the analysis. So thinking of this particular scenario, we could see that the information that is collected based on the expertise and the signal processing is also based on the expertise. And finally, with all this information, the meaningful things in his hand, the meaningful data, the processing, he would give the best prescription. And if you say that the industry 4.0 or the fourth industrial revolution or the use of the IoT concept is entirely biologically inspired. So the biological things that we see around us, we could relate it to that way, and also to manufacturing. So now I would present you a few operations. The first is the real-time control of a welding process to avoid the formation of welding defects. The case which we have taken for this application is friction stir welding. On the left, you can see a demo video of this process. So friction stir welding is a solid state joining process. This blue color thing is the tool. It's a solid tool, and here is a picture of how the tool looks like. The protruding part here at the top is referred to as the pin, and this pin is crowned by this shoulder. You can see here, this is the shoulder portion. So the materials are kept beside each other at the abutting edges, and this tool plunges inside the abutting edges, creating friction. That's why the first name of the process is friction. So the pin contributes and the shoulder contributes to the frictional heat generation, and after that the tool stirs over the material, and that's why the second name is stir. And with this friction and stirring, the welding occurs. Finally, the tool retracts out of the process, leaving a keyhole at the end, and this is the entire joining process of friction stir welding. So the need of monitoring in friction stir welding, the basic idea was to obtain a defect-free weld. And as it is the case for welding, because mostly the welding activities comes at the end of the process, so if it is defective, then the entire product product will be rejected. So it was very important to consider that how can we control the defects. The idea is that whenever we set an industrial context, we always use the optimum set of parameters, and those optimum set of parameters are obtained by doing a large number of experimentation. And whenever we have those optimum parameters ready, we always assume that we will be having a good quality product. But often there are several things, like there could be errors in the material itself, there could be some error in the machine health may degrade, or there could be some other noise sources. And this is why it may not happen that you always obtain a defect free weld. And this is the reason why the continuous monitoring of the process is desired to track all these things. May not be directly, but indirectly we would be having an idea that what is actually going wrong in the process. If you look at the current industrial scenario, most of the weld samples are either being tested in a destructive way by doing the tensile testing, or by identifying the grain size, or by using the non-destructive testing like RT or UT. And our objective was to replace the offline test. As I was saying, the need for monitoring the welding process is because we need to always obtain a defect-free weld. And as we know that from the experiments, we always get to know the optimum set of parameter combination. But in actual industrial practice, it happens that several things may go wrong. For example, in the case of friction stir welding process, since the materials are kept beside each other and there is a abutting edge, there could be errors in the material itself. If we think from a laboratory perspective, we can go and test the materials because they are of smaller size. But if you think of industry, the plates are long, and it is not desirable, or it is not possible to check each and every edge of each and every material. So there could be errors in the material. There could also the degradation of the health of the machine, or some other noise sources, which could lead to the deflection or the change the parameters that is obtained from the experimentation. And to avoid these things, to keep a track of these things, direct or indirect, we need to do the continuous monitoring of the process. And if you look at the current industrial scenario for welding, they either go for destructive testing, where they identify the tensile test, or the metallurgical analysis like the grain size or the distribution of the grains. They also go for the non-destructive testing like RT and UT. But our objective was to develop an online scheme that could replace this offline scenario and give a information about the product in real time. Just to give an information about the parameters that are involved in the FSW process, so they can be grouped into three. The first is the joining parameters that consist of the rotational speed. So the tool that I showed in the last slide, the tool is mounted onto the spindle of the machine, and the spindle rotates, and there is a rotational speed which is associated as one of the parameters. Now, as the tool starts over the materials to be welded, there is a speed at which the tool can be moved, and that is the welding speed. So the combination of the rotational speed and the welding speed is rate controlling, and it decides the amount of heat that is given to the material to be welded. And this heat is of course material dependent, and the type of tool that we are using. The tool is also given a tilt angle because the tool plunges inside the material, so it is always desirable that a tilt angle would ease the flow of the material from one side of the material to the other. And there is also a plunge depth where we ensure that the tool is in proper contact with the base materials. If the tool is having an improper contact, then the heat generation is always insufficient, and it leads to the formation of defects. Then we have the design parameters, which ensures that what is the design of the shoulder and the pin profile, their dimensions, and also the convexity or whatever we can provide to the profile of the pin or the shoulder, or you can have threads on the pin. So it depends on what is the type of the pin also. So they have different effect on the materials to be welded. And finally, we have the material parameters, which is like what is the material that we are taking for the combination of the tool and the workpiece, whether they are compatible with each other, and also there is a backing plate, which sometimes is important with respect to the heat that is generated in the process. So if I have to group it from the perspective of applying the Industry 4.0 or real-time monitoring, the joining process is the rate controlling and they are the online controllable parameters, while the design and material are offline controllable parameters. And why this is important is because, as I told, that the domain expertise is very important for going or to getting into the development of IoT or Industry 4.0 application. So unless we have the domain knowledge, we would not have an idea to know that which parameters are to be controlled and which cannot be controlled. And accordingly, we can design our experimental set and set other things in the scheme that these parameters could not be controlled, or how we have to take care of them in the scenario. So this is the slide where I'm going to discuss about the online system that we have developed for this welding process. And the first thing, as I told, is in the cyber physical system, we have the physical component, and here we, as the physical component, we have the welding machine. The welding machine has a controller which takes care of all the electronic components in the machine, and we have a computer which gives us a GUI system, the graphical user interface, where we interact with the machine for inputting the input parameters. From the FSW welding machine unit, we have a data acquisition unit which takes care of the various sensors data. Here we had load cells that collected the forces in the 3 direction, the spindle torque, the torque that was acting on the spindle of the machine. We also integrated several external sensors, like one of it was the power sensor, which collected the spindle power and the total power that was consumed during the welding. With all this information, the sensors data, we set up an edge device, and the real-time sensor data was transmitted to the edge device. Now, why it is called edge is because many of the manufacturing operation, I would say almost all, they need some time-critical decisions to be made. And for this welding process, a time-critical decision is that what is the quality of the process before even we could control it. So if we do not know the quality, which is very time-critical, we cannot make a control decision. And the edge device is termed as edge because it is located very close to the welding machine where the decision has to be taken. So it is at the edge of the physical device. So in real time, the sensors data using a TCP/IP communication system. TCP/IP is Transmission Control Protocol of the Internet Protocol, where the FSW machine was considered as the client and the edge device was our server. So in real time, we were communicating, or we were transmitting the sensors data to this edge device. And in the edge device, it is a small computing device where we had one optimized machine learning model that predicted the quality of the weld in real time. And this was our time critical decision, the getting the quality of the weld in real time from the sensors data. And once we had the predicted weld quality, we had a decision box that always checked whether there is a deviation from the desired weld quality. Now this is something which comes from the operator, how he is operating the machine and what is the end application of the product that is being manufactured, and accordingly he feeds his desired quality that he wants to achieve. And based on this decision, we take there could be, I mean, if there is a no deviation from the desired weld qualities, then the online system doesn't make any changes to the scheme. However, if there is a deviation from the desired weld quality, the online system takes the census data, that batch of census data which is coming in the real time, to a cloud where we had another optimized machine learning model. And that machine learning model
ఇది ఎన్విడిటి అంటది.
Participant, kindly unmute yourself.
God, sorry.
Can I go ahead?
Yes, please.
So, as I was saying that in the edge device, there is a decision box which was used to check whether there is a deviation from the desired weld quality, and if there isn't, it operated that was taking the census data as the input, and the output was that it predicted the optimized set of parameters that would be helpful for achieving the desired weld quality. And this is what this system has been filed as a patent with the Tata Consultancy Services on the real-time weld quality prediction and control also. So this cloud system, we had used the Megamara cloud of IIT Kharagpur. It is a private cloud of IIT Kharagpur, and we have also tested it with the Google Cloud systems. So in the optimized machine learning models, these are basically the deep learning models, neural networks. So one is for predicting the weld quality, and the other in the cloud is for predicting the optimized parameters. And one more thing that I should say about is the process twin. As you can see here, I've written the process twin. So you must have heard about the digital twin. So twin is something that is a replica of the physical product. So here the physical system is the welding machine, the welding process that is being taken care of, and this entire online system is acting as a twin for the welding process, because from the sensors data and all these machine learning models, the communicating devices that were transmitting the data amongst each other, and the cyber part, the physical part, we were able to get an indirect information about the quality of the weld that is going on. And that's why we call it as a twin of the process, and that's why the name process twin. This is one of the picture of test samples. As you can see, in the left side, there is a box in the red section, the red colored section, that shows there are various defects in the welded sample. There are voids, the surface is rough, and the voids are larger in size. So it is very obvious that if we use the defective portion, this red portion in anything, it would definitely be vulnerable. And we did this experiment by fitting the parameters in such a manner that a defective weld should occur, so that we could test the system. And from the sensors data that were collected during this defective portion, the online system take meaningful decision on the data, and thereby control the process so that the defects are totally eradicated. So from the defective portion in the red section to the defect-free portion in the green sections, this was done in entirely real time with the online scheme working on the census data. There is another picture of another weld where we started experiments with the optimum set of parameters to test whether there is any noise which is coming from other sources and is vulnerable to the online scheme. And as you can see that there was not at all any change in the parameters. The optimum set was followed from the start of the weld to the end of the weld. So there are a few more insights that we could gain from the online scheme. As I have told that there are multiple sensors that were installed in the process. So we tried to answer that is there any benefit of using the multiple sensors. And on the picture on the left you can see that when we also did the scheme with the single sensors, it is always the error is more, and the number of predictions required to reach the desired weld quality was always higher than the use of multiple sensors. Because multiple sensors, it is more amount of information. They may be redundant, but they help to achieve the accuracy. We also look into the use of both edge and cloud, because one can question that the entire thing can be done itself in the cloud. Why we need an edge? And this picture shows that when we were transmitting the data between the edge and cloud system, it always took less time to send it to the edge than to send it to the cloud. So if the entire system, both the deep learning models and the entire computing could be done in the cloud, but it would always take more time. And when it is the time is increasing, that means that the feedback would be delayed. So there would be latency in the data transmission, and to reduce that, we make use of the edge and cloud both. So what exactly is happening inside this entire IoT system? To show that, I have taken this one of the samples. Again, here there is a dashed line, and to the left of the dashed line we had a defective portion. To the right of the dashed line we had a defect-free portion. As you can see, this graph at the bottom, it shows that for the defective portion there was unsteady components in the signal. Here I have shown the force. This is the axial force information, and on the right we have the spindle torque that was acting on the during the welding process. And once it is defect free, once it is a good weld, the components, the fluctuation in the sensor components is very less, or you can say the components are very steady, or it stabilizes. And how we process this entire information inside the system is we used the wavelet analysis to operate on these signals in real time. So here I have shown two cases. One is the upper is the D1 coefficients for the defect free weld, and the bottom is the D1 coefficients for a defective weld. So if I have to say what exactly is wavelet processing, I would say in this manner. So if you are given an image of a scenery with mountain, sun, and several things like that, it's a big scenery. And as a human being, we always look at the bigger things in our first attempt. So we could see the mountains, we could see the sun, we could see the river if there is one in the scenery, because they are the more contrasting things. And then we also with time we also look at the smaller details in the scenery. So wavelets does something like this. It operates on this signal and decomposes a signal into several components. So D1, D stands for the detail, and 1 is at the level 1. So we could get different information at different levels. So there could be the detail components, which are the high frequency component or the fast changing things in the sensor data, and we also get the approximation coefficients, which are the slow changing thing or the low frequency information. And we were mostly information with the detail, because when it was a defective thing occurring in the process, we always had this idea that it is a fast changing thing. And here also we can see that for the defective to the defect free weld, the coefficients are the larger variations with respect to these two welding conditions. We also took a look at the energy that is being imparted to the welding condition with respect to the defective or defect free weld. And you can see that when there is a defect free weld, the entire energy remains with the approximation coefficients. It's close to 100%. But when it comes to the defective weld, the energy is reduced. There is a substantial change in the energy, and this entire information is actually curated in real time and is fed to the deep learning models that are developed to take this information and operate on the sensors data. This is a demonstration video for this work. So please let me know if you are unable to see this. Can you see the video?
Yes, we can see it.
So this is the picture of the welding machine. This is the friction stir welding laboratory of IIT Kharagpur. This is made by this machine is by ITA FSW Bangalore, and this guy on the TV, he is at Jamshedpur. He is at Ranchi, and he is taking care of the cyber part, and he could see the entire operation of the twin from his computer through the cloud operation. He's not doing anything, he's not operating anything, it's entirely remotely, but he is able to remotely get a feel of the welding process through his cloud device. So the material that has been kept here, these are two aluminum samples. The alloy is 6061 aluminum alloy, and this is a H13 steel made tool, and we have fed the parameters to the welding machine in a way that a defective weld was obvious, and the online scheme is now working, is also working with this, and you get to see what happens. So now the tool is inside the materials. Now the pin and shoulder is touching the base materials. Now this plunge, read is generated properly. And now this is the stirring. The tool is stirring over the materials. And you can see the material is getting removed because of the bad combination of parameters. And here you can see that. In the start portion, there is a defect. There are multiple defects in the portion, but the online scheme, there is a gradual improvement of the weld quality, and finally we get a defect-free product. This is how the twin was operating in real time. The second case study is health monitoring of a machine. This is also something related to the IoT application. So we call it a machine twin. So the previous application was process twin. As the twin, the replica was looking into the process information. And this twin, we call it a machine twin because now it is looking into the health of the machine. And to do that, we did a few instrumentation, like the force. The force was already, the load cells are already installed in the machine that were collecting the forces in the 3 directions. But externally, we also equipped the power sensor. That I told they were collecting the spindle power and the total power that was consumed during the welding. We also had the speed sensors that were collecting the speed of the motors that were responsible for the rotational motion, the spindle motor, and also for the feed motor. We also did instrumentation in the hydraulic line, the return line of the hydraulic systems. And you can see here this yellow thing is a thermocouple that was collecting the temperature of the oil. This is a turbidity sensor. This is for collecting the oil quality of the oil quality. And this sensor in black is a flow rate sensor that was collecting the information about the flow rate of the return oil. So one thing also I would like to focus or say is that these sensors are all Arduino based sensors. They are all low quality sensors, but the information that could be gathered from this low quality sensor can also be utilized for making information about the health of the machine. So the machine twin, as I've told, it is taking care of the health of the machine. So this machine twin acquired the sensors data in real time, and it was detecting the faults in the machine itself with the help of signal processing techniques, and it was also suggesting the maintenance action, as I told, is a part of its feedback. So this was the prescription that was done by the twin for keeping a track of the machine and also keeping it healthy, or at least not degrading it at a very higher rate. So this is a part of what twin exactly shows. So from the information that was collected from the speed sensors, it first shows the health of the spindle motor. So it's a very small mathematical model that was working at the back end. So let's say you have instructed the spindle motor to operate at some rotational speed. For this case, it shows that the instructed speed is 1000 RPM. So what exactly is the achieved RPM? Like for this case, the real-time achieved RPM was 997. So what is the performance degradation? Now, if I consider the machine twin working on this date, the calendar date, so what is the health of the machine at a later date? And we could always compare that is my machine degradation is going at a faster rate or the change is very slow. Now, if the change is very slow, which was of course for the case of this welding machine because it is a new machine, but when it grows older, as we know that health always deteriorates with time, this degradation would increase, and from there we can get an intuition that what exactly is going wrong and what we need to change, or whether there is need a predictive maintenance that is required for the machine. So this, from the speed sensors, we were able to track the spindle motor, the health of the spindle motor, and also the health of the feed motor. From the force and power sensor, we were able to track the health of the tool that was being used for the welding. Similarly, we had the entire idea of the health of the oil that was returning to the tank, because we had the temperature, we had the oil color which was giving the information about the turbidity, we had the flow rate, whether it is changing over the time, and we also had a level sensor which was collecting information about the availability of oil in the hydraulic tank. And I have a small audio. This is the twins feedback which is being collected in real time. I'm playing it for you.
Digital twin application started. Processing started. FSW tool health monitoring started. The values of wavelet coefficients of force signal is 380. The values of wavelet coefficients of power signal is 1023. Tool health currently okay.
So the force and the power data which were collected in real time were used for identifying the health of the tool through the wavelet analysis. And this was an online support vector system which was developed for predicting the quality of the tool.
It's predicted with 82% confidence. FSW feed motor health monitoring started. Under 100 millimeters per minute speed, performance degradation by 1%. Under 200 millimeters per minute speed, performance degradation by 1.5%. Under 300 millimeters per minute speed, performance degradation by 2.67%. If you would like to restrict speed always under 200 millimeters per minute, press 1, else press 0. User input. User chose not to restrict speed under 200 millimeters per minute. FSW spindle motor health monitoring started. Under 1000 RPM, performance degradation by 0.3%. Under 2000 RPM, performance degradation by 0.4%. Under 3000 RPM, performance degradation by 0.63%. If you would like to restrict speed always under 2500 RPM, press 1, else press 0. User input. User chose to restrict speed under 2500 RPM. FSW hydraulic oil level detection. Current oil level is 58%. No alert. FSW sensor noise level detection. Noise level of force sensor is minus 2.74 newtons. Noise level of power sensor is 41.6 watts. If you would like to subtract noise level from sensor reading, press 1, else press 0. User input. User chose to subtract noise level. Digital twin ends.
So this was the way the digital twin was taking the actions on the sensors data in real time, and it was also prescribing the information to the user about the health of the several components like the motors, the tool, and also the return oil. The next is the health monitoring of bearing. So what we did is we developed an entire mechanical system. This is a hydraulic assembly. We had here you can see this is a double acting cylinder, and the double acting cylinder is further instrumented with the proximity sensors. This hydraulic tank consisted of a motor and pump arrangement, and we were trying to install the bearings of discrete conditions at this stage. With the discrete condition, as in the bearings were having several faults like the inner S fault, outer S fault, there was a cage broken, and the jammed bearing. So at present we are working on this discrete cases. So we are using one bearing at each time and in this system, and we are collecting the sensors data like the vibration through the accelerometer. We are also collecting the power that is being consumed with change in the bearing condition through a power sensor, and this is the system that has been developed. So at this moment we targeted first looking into the data driven system so that we could classify the bearing faults in real time, but this is not our actual goal. Our main goal is to also derive the physics which is happening behind this system. How can we club the physics data with this sensors data so that we could build a hybrid machine to it. Just to give you a video of how the system looks like, I'll show. So this is a double acting cylinder which is operating the proximity sensors and within the sensor. During the entire process, we are guiding these bearings. We are also changing different experimental conditions, and we are trying to track the online fault classification system. At this stage, we have got some success with respect to the use of support vector machine, decision trees, and small machine learning algorithms that could be computationally very less expensive. But as I told, our main goal is to develop a hybrid system with this data and physics combined. The next operation is a robotic pick and place operation, and it's like we were trying to develop autonomous robotic application thing where the robot is doing several tasks by itself. Now, one of the thing which we were looking at, or the case study which we were considered, is how can the robot identify that what gripper it has to select based on the object which is coming on its way. So the problem is that the robot has to grip objects of different shapes, right? And this is the slide that curates that what exactly we were looking at. So this is the robot with the gripping system, and this gripping system depends on what sort of object it will encounter, and we have taken two discrete cases. One is the case one, which is a cylindrical type of object, and the case two was a cuboid object. So the problem that we were dealing here is the detection. So the robot has to detect the object which is coming on its way, and it also has to classify, and accordingly it will select that what gripper is necessary for it to pick that object, and once it has picked, it has to place at a different station. So station 1 is the manufacturing unit, which is giving the way forward to the products onto the conveyor belt, and on the conveyor belt the robot has to identify, it has to detect the object, classify, and then place it at the dispatch section. So this is the actual setup. This robot is a 500 kg payload robot. Of course, it is a robot for a different purpose, but we try to develop and implement this system in this robotic system. And as you can see, this is the gripper system that is fixed to the robot. It has a parallel gripper. This is the parallel gripper, and this was for the cuboid shape of objects. And on the right side, this is a 3-finger gripper. This was for the cylindrical objects. And with the first task being the identifying the detecting the object and classifying the object. The second was to identify the pose that was required to pick this cuboid shape objects. So this also we took as considered in our case study, because it is always not the case that the cuboid shape object will come in a proper manner or a very uniform manner for the robot to pick that object. They may come in different orientations. That's why it was very necessary for us to also get an idea of the pose of the cuboid shaped object, and accordingly the robot can be provided with the information like where the object is there and how it has to orient itself to collect or pick the object from the conveyor belt. So this is the picture showing the entire robotic arrangement. As I've told, this is the grippers. This is the webcam that is fixed on the robot. And one of the things that I would also like to focus here is that this is a webcam. Usually when we do some sort of image processing and deep learning, we make use of very expensive cameras, but we also targeted at developing this system for the small industries, and we thought how could it be made very cost effective. So instead of using expensive 3D cameras or stuff like that, we used a simple USB powered webcam which was collecting the information and doing this sort of analysis. So this is the conveyor belt, and there is this proximity sensor. This is to actuate the conveyor, actuate the robot, or to stop the robot and stop the conveyor according to by this proximity signal. This is the feeding station from which the objects were fed on this conveyor belt, and this was the dispatch section when the robot was picking the object from this and keeping there. And this is the manipulator. So as an IoT system, there were two things working here. One was the server. The server is attached to the robot controller, and it is collecting the information about the robot actuations, and all the robot variables were stored in the server. The client is the computer as another computing device which was having the entire image processing and the deep learning algorithms that were developed as a part of the system, and they were taking the information about the proximity signal, the stopping of the conveyor, and accordingly they were doing the analysis, and their feedback was that what would be the pose, what is the object, and how the gripper system that has to be taken by the robot to grip the object. So the communication between the server and the client was established by using the OPC UA. It is the Open Platform Communications Unified Architecture. So it helps. It is like a IP communication. So all the robot variables information we could see in real time in our client computer. The most basic thing behind the working of the system is the YOLO model. So we build the object detection model YOLO, and it works like it divides the image which is coming on its way in grids, and accordingly from each grid it collects the information and detects the object. So just to show a dog picture and how the grids are formed and how the information is collected, this is the real our experimental case, where you can see that there is a cuboid object and the grids are formed on the area which is available under the camera, and accordingly from each grid the features are detected and the object is classified. So this is the entire thing happening in actual action. Once the object comes in the camera feed, it operates, it uses the various image processing information to detect the edges, to detect the contour, and also to predict, to get the coordinates and the center of the object, and thereby we use the perspective transform to identify its pose and provide feedback to the robot regarding how to orient itself to grasp the object from the conveyor. This is the video. This is the part of work which we did at the IIT Kharagpur Center of Excellence. And as you can see, the red part is the conveyor belt. Here is the proximity sensors, that is for the actuation part. And this is the object that is being fed on the conveyor belt and the robot with the grippers. So once the object reaches the proximity sensors, it is identified that there is an object in the way, and that is when the proximity sensor gives a signal to stop the conveyor, and from there the robot camera takes the real-time feed. Sorry. So now the deep learning model is reacting, information is processed, and the robot orients itself and collects the object and leaves at the station. This is a cylindrical object. So now the robot has changed its gripper system. So I'll move forward. So this is the way the entire actuation thing is working here. It's the YOLO model and the image processing algorithms which are working with the robot controller to actuate the robot and provide it feedback with the pose. This is another work which is determining the condition of the cutting tool in the machining process. Well, what we identified as a problem here is that most of the methods that have been provided for detecting the cutting tool condition are machine specific. By machine specific, we mean that they are not translatable from machine to machine, or the features of the signal processing methods, even the machine learning things that are developed are not translatable, and many solutions that are being regarded nowadays are expensive. They make use of multiple sensors, huge amount of data and deep learning solutions, and also they are trained on the historical data. When things are trained on the historical data, it gives a perspective to know about the previous condition, and what we have to know is what exactly is the present condition. And that's why the supervised solutions can be a problem when it only is trained on the historical data. So how to leverage the present condition, how to make use of the present data with the historical data, so that the intelligence of the model or the learning of the model is enhanced each day. So what we propose is to develop a solution that should work across different types of machines, different varieties of machine, be it could be smaller machine, larger machine, different materials, various type of processing conditions, and it has to be low cost. It should make use of at least one or at most two sensors data, and whether we could develop something unsupervised type of task, so that we did not to be dependent on the historical data, or we did not to dependent on the training of the historical data, it should take the information as it is coming from the data in real time and makes an informed decision about the condition of the cutting tool. So our experimentation include these different machines. As you can see, the machine 1, it is a Haas-make machine. It is a mini mill, sort of tabletop like thing, but it is mostly used for semi-production, small size objects, and has a very smaller footprint. The second machine is the Mezak made. It is a 5-axis VMC. It is for small to mid-size objects, and it is a larger footprint area than the machine 1, and it was having larger capabilities also than as compared to the machine 1. The third is a hybrid additive and subtractive manufacturing machine by the DMG Mori, and it is mostly for the production type of jobs. And with all these three, we took different configurations of sensors, like the mechanical sensors. There were the force and vibration. Even the force we collected from the stationary sensor, from the rotating sensors like the rotating dynamometer. Then we have the electrical configuration sensors, like what is the change in the current, the voltage, the load acting on the spindle, the total power and the spindle power. We have temperature, which is the temperature of the workpiece and also the temperature of the cutting tool. And we had the video and audio sensors data. And all together, our objective was to collect data from one or best two sensors. It could be cost-effective solution, and how can we detect the cutting tool condition at this stage to go for a data-driven digital twin for the cutting tool and also for the machining process. As I told, the data is coming from different distributions. As you can see here, the histogram plot reveals that the data is differently scattered because it's coming from different types of machines. The process being the same, but they vary amongst each other. And what we proposed as a solution is that instead of working on the raw sensors data or operating from the perspective of signal processing, why could not we window it? And window it in a manner that we could extract some features out of this signal, and these features were the mean, RMS and the variance. And these were taken because we were working on the vibration and power data, which are cost effective, and the vibration is like, as the cutting tool condition is degrading, the vibration is sort of intuitive and it should increase because it would create more friction among them, the rubbing action. There would be less of cutting, more of rubbing with the deterioration of the cutting tool, and these features would sort of represent the vibration signal, and we windowed it according the sampling of the signals and the windowing. We worked on different frames of the window, and this running window gives us different features for the signal, for the vibration and the power signal. Now, when we had these features, it represented a case of multivariate statistics, and to work on the multivariate statistics, the different machining runs and these features, we use a distance metric that was working on this multivariate statistics. This distance metric, like Euclidean distance, Mahalanobis distance, and other Manhattan distance metric, to work on those features and collect or identify a health indicator that is more informative of the cutting tool condition. This slide shows the computation of the indicator and the ranking of the sensor, and as you can see that irrespective of the machine size or the parameters or the type of material they were used to machine on, the distance increases as the cutting tool goes from the inception of its life to the end of its life. So there is always an increase in the distance, and this is so because the degradation in cutting tool is so that the distance increases, the signals vary, and these features distinctly differ from each other because of the changes in the cutting tool condition. We also found that the vibration signal is very much informative about the cutting tool condition, and the Mahalanobis or Euclidean distance can make use of the features to provide you a better indicator about the cutting tool condition. Now, when we have all these features in hand, we could make use of very cost-effective algorithms. Like I've shown a case of k-means clustering, where you could easily cluster the data and give the operator and a small information about the life of the cutting tool. So at what stage it is. Like in this case, if I take the cluster of this, the tool wear is lying between a range of 0.0024 to 0.05 mm. So this gives an idea to operator that it can still go this many runs. Or if I go to this region, this is the critical region, the green ones, and we identified thresholds based on these different clustering algorithms, and those thresholds were working across the machine and gives an idea that it could be used irrespective of the machine sizes. So these were the case studies that I wanted to discuss about. And finally, I would like to give the way forward is that we have to make use of this DIKW pyramid, which in fact shows the application of machine learning at this stage. But if you consider all the things in small crunches, then it would go for the development of the of an AI system. This knowledge pyramid is what we have to look into. How can we get the data from the system? Because data is the fuel, it is the raw material. Without data, we cannot operate on these things. So once we have the data, how can we apply the signal informatics so that we could get what, where, and when? So that gives us the context, the data that we're collected. So once we have this information, we could do the descriptive analytics, or we could describe the process. For example, if you look into the welding process, from the process twin, we collected the wavelets, the D1 coefficients, the detail coefficient, the approximation coefficients, those energy that gave us a context whether the weld is getting defective or the weld is defect free, and where exactly is the defect, because we were time localizing the signals. So that was a descriptive analytics of the weld. From that information, we could take those detail coefficients or those information that is derived, the meaningful information, and we could develop the models, the knowledge, and we could semantically represent those. So that would give us the diagnostic, because it is more of like we could now automate the process with this information. And when we have developed these models, the context, we could understand the what if scenarios and do the prescriptions, which is from the digital twin perspective. So it gives the wisdom, and in that way we could diagnose the process and also have prescriptions. So it's both diagnostics and prognostics, and this is known as the knowledge pyramid. I would like to say that you can refer to this book, The Digital Twin Fundamental Concept of Applications in Advanced Manufacturing. I am one of the co-authors in this book, and it gives a whole lot of idea about the application of digital twin, the concept of IoT and cyber physical systems. And the uniqueness of this book is it builds on the fundamental theory, but it also discusses the relevant case studies in manufacturing. It contains more than 50 case studies. So it talks about the various sensors that is applicable to manufacturing, the signal processing and image processing methods. It also speaks about the machine learning methods, and finally how we can develop the digital twins, the machine twin, process twin, and how we can emulate the signal processing and image processing information in the twins to make the descriptive and prescriptive analytics for the operations. So with this, I would like to conclude my presentation. Once again, I would like to thank Dr. Krishna for giving me this opportunity to speak at this beautiful platform. I would also like to thank Dr. Kumar, the HOD, for setting this event. And if you have any questions, you can ask me, and you can also give me suggestions on my presentations.
Yeah, thank you, Dr. Debashish. It was a very well planned and nicely organized, very informative session. We enjoyed it very thoroughly.
Thank you.
Participants, if you have any queries, please don't hesitate to ask him. Feel free to ask him any question, even small or big. Debashish, I think you have one or two questions in the chat box. Maybe you can see it.
Okay. We being mechanical engineers, we can do machine learning algorithms, but what about digital image processing? How can we get it DIP? how can we get it digital image processing? Is that the question? Uh, I'm not sure about what exactly the question is, but if I infer it in this way, that the question is, how can we learn about image processing or signal processing? So, if the question is this, it's very straightforward answer. You have to take a course on signal processing or image processing and get the basics of signals and systems. So if I have to say about the signal processing, I would definitely say the fundamental course is the signals theory and systems, which gives us an idea that how the signal is look like, what is exactly the signal behavior, how the signal is processed, how it is sampled, what is the time information, frequency information, and thereafter we can see something like the use of wavelets, which is at a very higher level time frequency information. So the techniques remains the same. If you also go to the digital image processing, you also make use of wavelets, pyramid techniques. So you need to take a basic course, of course.
Any questions from the audience?
So please send your textbook. I will send the textbook. Maybe I can send it to Dr. Krishna and sir.
Yes, that's better. So apart from the book, any questions from the audience?
Sir, am I audible?
Yeah, you're audible, please.
Hello. Yeah, Devashi sir, your presentation is good, sir. I'm very much interested on your work. And I have one question, sir. How your machine learning is useful to monitor FSW machine with IoT, sir? How a machine learning, like algorithms, example?
Yeah. So if you see that when we were processing the information from the sensors data, that is the use of we use the wavelets to identify the variation in the coefficients with respect to a defective weld and defect-free weld. What we had the information in hand is, when there is a defective weld, there is change in the wavelet coefficients. When there is a defect-free weld, we had this range of wavelet coefficients. But this is the signal informatics. If you remember in the knowledge pyramid, the second part. But how to automate the process? We have to make use of machine learning models to automate. So we had different scenarios of welding defects, be it the voids, be it the surface voids or larger voids, smaller voids, the difference in the gap in the welds, and all those information that we collected with respect to the different scenarios, we automate the process in the machine learning model. But if you're asking what sort of models we built, so our was a neural network that was trained with the gradient descent. It was a back propagation neural network, and the optimization was done with respect to the genetic algorithms.
Okay, sir. Okay. Sir, any application of this IoT in your work, sir? No, I'm sorry, but machine learning algorithm. What algorithm you are using?
So for this FSW case, we use the smaller machine learning models, like we use linear regression, we used decision trees, we even use the random forest, and we were particularly operating on those smaller machine learning algorithms to see whether how much benefit we are getting from developing a deep learning. So we started with very basic like the linear regression, and we see that where exactly the models were failing, or what was the conditions in which the models were unable to decide on the parameters. I would also emphasize, when we are going for such analysis, decision tree and random forest are useful, because when the tree is formed, we get to know that which features are the most dominating, which features are the most important, and how the learning is actually starting with respect to the use of decision tree, the tree that is formed. And based on that, we could also realize that where exactly is the model getting failed, whether it is trying to duplicate some information, or whether it is unable to differentiate between two scenarios. And there itself you will get to know that when a deep learning model is most suitable for the application, and machine learning model would work.
Okay, sir. Okay, thank you.
Okay.
questions from the audience? And small information, feedback link has been shared in the Google chart itself, meeting link. So you have to fill this form.
Please suggest any other books on applications of IoT and mechanical engineering. I don't remember the author, but I have two books. I'll definitely share the links with Dr. Krishna, and sir, please share the books with the participants.
Okay, sure.
So there's a very good book which speaks about the IIoT applications, the industrial environment, and how you can leverage the IoT devices. I'll definitely send the book.
Sir, one last question, sir.
Sure.
This is Praveen only again.
Sure.
Yes, how much approximate cost you spend for IoT with the festival? Like sensors, algorithms, all these works.
Okay. So if you talk about the process twin, the machine, I'll not speak about the cost of the machine because the physical systems are always very expensive. But if you have a physical system, the cost of sensor, what we have used, the power sensor are somewhere around thousands. It's a 7,000 rupees, the cost of the power sensor. It comes along with all the necessary cables and the data acquisition systems. The cost of a computer, now the cost of computer would depend on what sort of computing you need to require. For our case, it was a very small, the edge device is very small. It's, I think 8 GB computer. So the other cost, which was about the use of the cloud, and that also depends on how you want to configure a system. So the Google Cloud, I do not know what is the scenario right now, but when we used it in 2020, as you once start using Google Cloud, it gives you 20,000 credit points. That's free for around 6 to 8 months, good to go. So you can use a small sensor, a small computing device, and a free Google Cloud platform for your IoT application.
Okay, sir.
Any other questions from the participants? If there is no questions from the audience, once again, thank you very much, Dr. Debashish, for your well-made presentation and to enlighten us with your sound knowledge on this topic. We expected much more sessions from you in nearby future and all.
Sure.
And once again, thank you very much for readily accepting our invitation and sharing your knowledge in this online session.
I am very much thankful for the opportunity. Thanks a lot. And thank you to all the participants who have joined today. And thank you, Dr. Kumar, in this event.
Thank you, sir. Thank you, Mishra ji. Thank you so much, sir. And your presentation is excellent, sir. And you covered all the topic from the fundamentals of Industry 1.0, 2.0, from that point to the recent advances. Beautiful presentation, sir. Thank you so much, sir, once again.
Thank you.
Thank you, Dr. Devashish. This is Satyanarayana, one of the participants.
Thank you, sir. Thank you.
Satyanarayan, sir, you can introduce yourself.
Okay, fine.
He is the head of the department at PVPSIT Guntur, sir, Engineering College.
Oh, wow.
Yeah.
Thank you, Raghu, sir. And once again, thank you for this session, and very informative one. And from the book which you are supposed to send, we will gain the knowledge, and we will guide our fellow faculty as well as students in this area.
Sure.
Okay, sir. Thank you, sir. Thank you. We'll close this.
Dear participant, kindly fill the feedback form before you leave the meeting.
Okay, thank you all. Thank you all the participants for your patience listening and and also the doubts you are asking. It is definitely is encouraging for us and to conducting the sessions like this. Thank you all, and good night to everybody, and we will meet tomorrow at 6:45 p.m. Thank you all.